Hello, everyone. My name is Jimena Aguilar Vega. I'm a PhD at the University of Stirling. Welcome to the Cryosphere Pavilion and this event on connections between Arctic sea ice, laws, and European weather. Let me introduce you to Mark Ceres, Director of the National Snow and Ice Data Center. Please, Mark.
Don't think the microphone is on. Is the microphone on now? Ah, there. An improvement already. Well, greetings, fellow concerned citizens. This is a very interesting topic we're going to be dealing with now. There's been a lot of work, at least over the past decade, about possible connections between the rapidly warming Arctic, particularly the loss of the sea ice cover, in terms of enhancing what we call Arctic amplification, the outsized rise in temperatures over the Arctic compared to the rest of the planet. There's been a lot of work arguing that outsized warming could actually influence things like the jet stream patterns, which could influence weather patterns in middle latitudes, in many different parts of the mid latitudes, over Europe, over North America. It's been a very controversial subject. There has been some scientists saying, oh, absolutely, this is happening. I see it now. Others saying, I don't see the evidence. Others saying, there is something there, but we're not quite sure. And so I am pleased today to be able to introduce Alistair Skelton, who is the co-director of the Bolin Center in Stockholm University, who will provide you with a new perspective on this issue. So, Alistair, the podium is yours.
Thank you very much indeed, Mark. Thanks for the warm welcome. And nice to see you all here in Glasgow. And I also like to say hello to everyone following in Geneva and also following in Stockholm. So I'm going to talk to you about European weather. And one will wonder why I'm going to do that at a Cryosphere Pavilion. And I'm going to take us there through these slides. So a few statements I'd like to begin with about European weather. And these are from various papers presented at the World Weather Attribution Project. It's virtually certain that the heat wave that stretched across much of Europe in 2015 was more likely due to climate change. Climate change increased the chances of seeing a summer as hot as 2017 by a factor of 10. The probability of such a heat wave, and this is referring to the Northern European heat wave in the summer of 2018 to occur, has increased everywhere in this region, again, due to anthropogenic climate change. Summing this up, every heat wave in Europe in recent years, and that's 2003, 2010, 2015, 2017, 2018, 2019, I'm not missing many years out, am I? Was made much more likely and more intense due to human-induced climate change. This is where we are today. This is warming in Europe. This is warming measured at 17 different weather recording stations around Europe in different cities. The warming here has been corrected for urban bias. That is, cities are simply warmer and they get warmer as they become bigger. What you see, the take-home message from this slide is that 1 degree warming globally, which is what we have, 1.1, 1.2, means 2 degrees in Europe. 2 degrees warming in Europe. So it's happening faster here in Europe. Why? Why is it so? Why is it warmer in Europe? I'm going to tell you about a study, curiosity-driven science. I've done my work mostly in statistics, working on earthquake forecasting. And I thought of applying the same statistics to weather data just on an exploratory basis. I began here. This is Stockholm Observatory in the middle of the city of Stockholm, and this is a place we've been recording recording main annual temperature for a very long time, back to 1756. And it's been written actually on the walls of the building inside the observatory. It's quite fine, actually. These are the data, and that's starting in 1756 and then carrying on until the present day, with an 11-year moving average shown just to make it a little bit easier to visualize, so we get away from looking at weather and start looking more at climate. So basically, not an awful lot happens for most of this time. It goes up and down a bit, but there's not an awful lot of change. There's a point here where something appears to change, some kind of abrupt change, and then the temperature starts rising quickly. But anyone working in statistics would not be comfortable with saying that there's anything significant happened there based on that curve. Has something happened? Has it not happened? I put lots of arrows on that slide. It drew your eyes to it and you start seeing it. But is it real? Here's a few other stations: Uppsala, Prague, Münster, and Verona. An almost slightly cooling trend, or no change at all. This apparent, seemingly abrupt change, and then the temperature starts to rise. And I've shown you 4 examples. We looked at 17 sites. They all show this trend. And in fact, so does Blue Hill in Observatory just outside Boston in the US. But can we see this abrupt change more clearly? Is there a better way of looking at this, that we can take away weather so we can start looking at climate? So we're looking at the longer term. Oops, sorry. That slide just... One way of doing that is to look instead at histograms of temperature data. And I've color-coded these histograms for the same 4 cities, so that pale green are the years before 1901. Intermediate color green, then we're going from 1901 to 1990, and then after 1990 is in dark green. And and it doesn't look like it changes very much between before 1901 and 1901 to 1990, but you do see that the after 1990 data are skewed to the higher temperatures. That's not too surprising. It's a warming world. Using the skewness of a histogram is a good way of taking away the year-to-year weather variation and looking at the longer-term trends. So if we look, I now just got before 1901 again. The hypothesis is, in the 1901 to 1990, there's a slight shift to cooler temperatures. Moving forward, there's a strong shift to warmer temperatures. Now, that shape of that curve, the tails, can actually be measured and quantified with a parameter called skewness, which just describes how lopsided is that, how top-heavy towards the warmer years. And we can look at how it changes with time. And in the study I'm going to show you data from, we did this in 17 different sites in Europe. Most of them are single sites, except for one which is called Hadley, which is a combination of a number of different sites, and is actually the longest temperature record we've had to work with starting in the mid-1600s. And these figures show the skewness and how it changes. What we see when we look at this is this brings out there's little. I'm apparently allowed to carry on talking despite of that noise. And what we see is slow cooling and fast warming. And there's a very abrupt transition. Now, the reason it's clearer on this figure is I've taken away the year-to-year variation by just looking at the skewness of all of the data. It's only possible to do this type of analysis when you've got a lot of data. That's why the study's done in Europe, because we've measured temperature for so long there. And it's not really possible to do in many other places, although we have succeeded in Blue Hill in North America. And then we find these abrupt changes, and they're pretty and these are the best fit years that they occur. Uppsala 1999, Prague 1989, Munster 1993, and Verona 1990. And we actually looked at a lot, and this is now showing all of the data, all 17 sites. And we see that the main, with 95% confidence, is of that abrupt change is between 1985 and 1991. And the median is 1990. So I'm going to use 1990 when I move forward, but that's the median. Remember, I'm also referring to a slightly broader range, but for simplicity in the rest of the talk, I will refer to an abrupt change in 1990. So what's the cause? Well, there's lots of things you can look at. In our study, we were able to rule out what's ocean circulation patterns, and I'm not going to take time with that because I don't want to use much of your time. But one obvious thought is sulfate emissions reductions in Europe, and actually also North America. There were major efforts to clean up the fuel we were burning, and that caused a drop in the amount of sulfate particles being emitted. So why does that matter? Sulfate particles are like small mirrors. They reflect away heat from the sun, and they make the earth cooler, which means when you take them away, the earth gets warmer. So this is what the sulfate emissions curve looks like for Europe from 1900 up until the 2000s. And what we see is a fairly strong increase, peaking, and then it drops down again. The peaks run about here, and that's where the reduction begins. And that's about 1975. Now, that doesn't match perfectly with our 1990. It's a bit earlier. So one can ask, is this reduction in sulfate emission something behind the accelerated warming? Maybe. But the timing is not a perfect match. So now let's look at the melting of Arctic sea ice. And I want you to look at this video because this video is from NASA and it is showing Arctic sea ice. It's color-coded for thickness. So the white is the thickest parts. It's going to take us from 1984 to 2016. And I think out of respect for what we're doing to Earth's climate, I want you to just look at it and feel this. This is everyone around us was probably born before 1984. This has happened in our lifetimes. The reason it pulsates is that's year to year. That's annual. But just watch how it disappears. The Arctic sea ice is reflective. It's like a mirror. In the summertime, it reflects the heat from the sun. It makes the Earth cooler. When it disappears, it can't do that anymore. Arctic sea ice, loss of Arctic sea ice is already responsible for 0.1 degrees of global warming. When it's all gone, it will probably be responsible for 0.2. It's about half gone now. So this was where we were 2016. So what about that melting of sea ice? Well, this is the Arctic sea ice extent. That just means how much of the Arctic was covered by sea ice at the minimum, which is September. And we look at that data from 1900. And these are measurements. It's a very abrupt where it starts. That's where melting begins. And that indeed is around about 1990. Now, working with statistics, coincidence and timing is not a proof of a cause and effect, but it certainly supports it. It certainly argues in favor of the Arctic sea ice having an effect on what's going on here in Europe. The image didn't show up, but never mind. It's a pretty image as well. That's a shame. Reduced sulfite emissions, coupled with melting of Arctic sea ice, are likely causes of accelerated European warming. I can't separate them both, but there's a real the reduction in the sulfates makes the Earth warmer. the melting of the Arctic sea ice makes the Earth warmer. Those two effects together could well be behind what we're seeing going on in Europe, as they affect us. The most important conclusion, what happens in the Arctic, that affects us all. We need to act now. We need to act now to keep 1.5 degrees within reach. Thank you very much.
Questions. If you have questions, please come up to the podium. I have one myself. I'll go to this one because it's a little easy. I'm too tall. That's the problem. Is this one working? Oh, yeah. It's interesting that, of course, I've been looking at these records and things like this, is that one of the things we saw coming up in the 1990s was the North Atlantic Oscillation shifting, okay, to a more generally positive mode. Now, it's always bad to talk about trends in atmospheric circulation patterns because they invariably go away, okay? But when you saw this warming was pretty much at a time when we were shifting positive, okay, which we know over Northern Europe has a warming signal, okay? So can you comment on that, at least part of this initiation in terms of natural variability?
Yeah, to comment on that, there is interference when you to comment on that. Yeah, that is also a potential likely effect. And the take home from that is these systems are so heavily connected. When you start messing around with the cryosphere, the oceans, putting carbon dioxide in the atmosphere, you can expect that all of the systems are going to respond. I think that that question underlines that what happens in the Arctic affects the rest of the world.
But now I'll ask another question because I'm interested. I'm interested in this.
No, I'm not hearing you. Hold on.
You're not hearing me. Are you hearing me now?
I hear you much better. Yeah. Let's just do it.
What was the question now? What was my now you lost my train of thought for a minute. Yes. But when you're talking about a link with sea ice here, okay, what is that link that you're talking about? I mean, are you talking about a dynamical link? As I said in the introduction, right, there's been a lot of work saying that there's dynamical atmospheric links with this. For example, the loss of sea ice has some effect on the jet stream patterns, stratospheric linkages, and like this. I mean, you've kind of told us that there's possibly a link here or a correlation, okay? But where would that come from? What's the basis of that agreement, you might say?
I look at this very simplistically. And my immediate answer to that is that there's an albedo feedback. You start losing the ice, and the Arctic ice in summertime is serving as a mirror, and it's just because it's such a large area, it is serving for 1/10 of a degree of warming. It's going to be more felt up there. So I would call if I had to speculate, I would call an albedo feedback, an albedo being reflectance.
Yeah. This is very other questions. People have other questions here, and please come up, please.
So I know pumping sulfate emissions into the atmosphere has been proposed as a potential geoengineering solution to cooling the planet. So I'm just curious about how you propose to balance some of the problematic outcomes that come from pumping sulfate particles into the atmosphere, but also balancing that with some of the solutions that can provide for mitigating ice loss in the Arctic and increasing albedo of Earth overall.
There's going to be a session later on today on the terrifying topic of solar radiation management, which is a delicate way to say that one would manipulate the albedo of the Earth, making the Earth's atmosphere more reflective, basically mimicking volcanoes. Mount Pinatubo, during its eruption, cooled the Earth. And it did that by putting a lot of sulfate particles up in the higher parts of the atmosphere. That adds a mirror effect, and it makes the Earth cooler. There is a long list of risks associated with doing that, and risks that have been quite frankly confirmed by in the geological record. After Pinatubo, what we noticed was a massive drop in rainfall. A massive drop in rainfall means failed crops. It means a loss of food security. Laki, I think many of you will have heard of the Laki volcano, 1783. It describes emission of sulfate particles to the atmosphere, not in a bit of a bigger scale than is proposed for solar radiation management, but not that far off, and that was followed by a sulfurous smog that damaged crops, and people died. For me, it's a different topic. This is a topic about reducing sulfate emissions, and that's the idea of adding sulfate emissions to somehow make our climate cooler. It's a naive and a scary approach with all sorts of damage that's going to cause. I mean, I could rant on this for ages, but one last rant is that the other thing is it's a commitment forever, because once you stop dealing with the problem, which is carbon dioxide, which stays in the atmosphere for thousands, tens of thousands, hundreds of thousands of years. The only thing that takes CO2 out of the atmosphere for long term is the weathering of rocks. I'm a geologist. I look at rocks. They weather slowly. If we take our eyes off that as our solution, emissions reduction, start looking at ways of cooling the Earth, the emissions just carry on going up. The CO2 is still there. And when we ultimately stop modifying the atmosphere, the temperature will rise very, very fast. It's called a thermal shock. It's bad news. Thank you for the question.
Other questions, please?
Thank you very much.
I can't really hear you.
No, maybe I can. Okay, thank you very much. So I do not like to say that, but I'm not fully convinced by your arguments. So I think that you raised very good points in terms of statistics, but there are now many available tools, for example, performing numerical simulation with climate models, which would be very useful just to test your different hypotheses. It's relatively easy to do now. And so it's just an advice that you should do that. And then you will see whether one of your hypotheses work well or not, or if it's just because greenhouse gases are increasing. And so we are entering in a new world, and it's warmer, and sea ice, hot temperature in Europe in winter and summer, and they work together, but maybe they're not the cause of each other. So
I think that's a very fair criticism of the study, but I'd like to underline the purpose of the study. I'm a data person. The data points to an abrupt change happening. I throw that out in the community to work with. A plausible link is the melting of the Arctic sea ice. I agree entirely that the way forward is to start modeling that and see if it can really be supported. Couldn't agree more. Thanks for the comment.
Well, I could actually comment a little on this. I mean, if you look at this in the very simplest way in terms of a possible sea ice link beyond just warming, is to think about how our weather system works. Okay, you've got more solar heating in the lower latitudes than you have in the higher latitudes. That's a temperature gradient of the atmosphere, a pressure gradient of the atmosphere. That is what drives the atmospheric circulation. So every time a low pressure system goes through with its warm front and its cold front, it's doing its job of transporting heat from the lower latitudes to the higher latitudes, all right? And this is why we have stronger storms in winter than in summer, because that differential heating is so much bigger in the winter. But now imagine the idea is that you'd have some kind of process that gives you a strong Arctic warming, lose the sea ice, and so you're pumping all this heat into the atmosphere in the cold season. You're changing that temperature gradient. Okay? If you change that temperature gradient, the argument is the atmosphere has to respond to that. How will it respond? Okay? It could do so in a very complex, very nonlinear way involving a number of stratospheric linkages which have been proposed. As I say, it's a controversial thing, right? What is happening? I don't think anyone is saying there's nothing there. The question is, how strong are these effects of a strongly warming Arctic versus other things? And for example, could part of the strongly warming Arctic be in fact due to changes in atmospheric circulation? So it becomes a bit of a chicken and an egg. I don't think anyone's denying there's a link between Arctic sea ice loss and weather impacts. Okay, the question is, how does it exactly work? What's really the mechanism there, right? And how strong is it? At least that's my view, my understanding of it. Yeah.
Thank you very much. I agree. Fascinating, a great place for great opening for further research and understanding. Worth bearing in mind that we don't have much time. We as researchers need to carry on working on solving, trying to understand. That's what we do. But we're also sending a warning at the world that there's an abrupt change there in the data. We'll have solved it, worked it all out 10, 15 years maybe from now.
Yeah.
I wouldn't wait. I just reduce emissions now.
Yeah. One thing I would just add to this too, in terms of the impacts of an Arctic warming on weather systems in mid-latitudes, is that's going to be influencing precipitation patterns. If in fact that occurs, that influences precipitation patterns, and that's where some of the real importance comes from it, like in wheat growing regions and things like this, right? That's where I'm just saying that's where some of the real effects could be. But it's a very, very active area of research. I read a paper a few months ago that says, oh, there's nothing there. Then I read another counter one just very recently saying, absolutely there is. So it just goes to show you that's how science works. If we knew everything, it wouldn't be called research.
Absolutely.
Any other questions? Oh, please.
Yeah, thank you, Mark. Thank you. This is actually a follow-up question on the polar jet stream. So it's just to continue on that topic. So the question is from David Bolton, who is following us online. And his question is, following on the jet stream question, what effect will be expected on ocean currents? So I think David is asking the connection between atmospheric changes and the oceanic changes. He's asking about the Gulf Stream in particular, and what is the expected climate influence on Europe if something happens to the Gulf Stream?
Well, David, I would love to be able to answer that question. I am not an oceans scientist, and for me to do so at the COP would be naive. I do have colleagues who are working on that at the moment, and interestingly, and I will just quote what one of them said. It said, "We'll have worked that out when it's too late."
The only thing I can add to that is that
can you answer that? Maybe you can answer that question.
Yeah, well,
for me.
I can add a little to it, that at least one of the responses that has been suggested from model studies, of course, models are wrong, some are useful, right? Is some of them are showing a positive NAO response. It'll kind of tip you towards a more positive mode of the NAO. Now, if that's the case, that is definitely going to have influences on things like ocean temperature and things like that. But as a matter of fact, some of the very original work on this was pointing to that. But we will see, right? The thing about atmospheric responses is these responses can only be so big. No matter what happens with global warming, the Earth is still turning. There's still a Coriolis force. There's still differential heating. There's still the land-ocean configuration. So only so much can change, right? But something like a shift in the NAO could certainly have considerable impact on, say, Northern European climate.
Thanks.
All right.
Thank you.
All right. Any other questions here? This is a good discussion we're having here.
This is
very vibrant. Yes. Other questions? Yes, please.
Sorry to hop back about the ocean, but you did kind of dismiss the role of the ocean early on in your talk, saying you don't want to talk about it. But could it not be that the ocean drives the whole thing? that warming ocean has just caused a warming in the Northwest Europe.
We looked at AMOC as that was our first hypothesis. And we found a really, really poor match for AMOC. So our data doesn't support that. That doesn't mean it isn't the case, but our data does not support that at all. It was with the, now I showed with the sulfate emissions reductions and the Arctic sea ice, we have a stronger argument, but I can't rule it out. And I wouldn't want to do that, but I've got no data to support.
Cool. All right. Other questions? Other questions? Going once? Going twice? All right. Well, thank you, Alistair. This was great. This is very, very valuable. I think we got some good discussion going on this. It is a very controversial issue, right? These sort of links, and we have to study them.
Thank you for all the great questions. It's been really, really nice. And it's lovely to hear a lot of science going on here at the COP. This is really, really
we
good.
love science.
Yeah, we all love it. Thank you for everyone who's following online. And goodbye from Glasgow.